Okay, in the previous video, we went over the relationship between delta G non-standard and Q, and in relationship to this U-shaped graph here, like where you're at. So in this video, we're going to be concentrating on this side of the graph where you have way more product than you do reactant. Okay, and we'll see that we're in the example I provide, we're going to start like right here, and then we'll see what the reaction needs to do to get right here, which is from the previous video, which was equilibrium. Okay, so I'm going to use this reaction. I'm going to use the synthesis of ammonia, where you have nitrogen gas and hydrogen gas coming together to make some ammonia gas. And delta G, so I'll do the work down here. So delta G non-standard equals delta G standard plus RT ln of Q. Okay, I'm going to write Q right here so I can analyze it as I go through this example. So it's the partial pressure of ammonia gas squared over the partial pressure of H2 gas cubed times the partial pressure of N2 gas. Okay, so here are some numbers that I'm going to use. I'm going to start off with like a really big amount here, and because I want to establish this situation where Q is greater than K. So I'm going to use like 2 atmospheres, which is a lot of the product. And I'm going to use 1 times 10 to the negative second atmospheres for H2. And for N2, I'll set this equal to 1.47 atmospheres. Okay, so, and I went ahead and I looked this number up. It was negative 33.3 kilojoules per mole. Okay, and we're going to see that this, so delta G, remember right here at this point here, delta G non-standard is going to be 0 at this point right here. So here's where delta G non-standard is 0, is right here. Okay, and we'll see that under standard conditions, if everything were 1 atmosphere, this whole term right here would be 0. And then you would be, delta G non-standard would be equal to delta G standard, which would put you like around right here or so. But I'm not having 1 atmospheres. I'm going to do a whole bunch of product, okay, and very little reactant, especially with the H2 here. Okay, so let's see where that takes us. Let's see where on this chart here we're going to end up. So this, as the title of the slide implies, we should end up like over here somewhere. Okay, so R is 8.314, and we need to convert that to kilojoules times 10 to the negative third. Temperature, we'll do this at 298 Kelvin, and then ln of Q. So Q is going to be 2 squared over 1.00 times 10 to the negative second cubed times 1.47. Okay, so let's pull up the calculator and see where that takes us. So and my calculator, I'm just going to do the RT ln of Q term and then see how it compares to this term. So in my calculator, I'm going to do this piece right here and then see how it compares to this term here. So 8.314 times 10 to the negative third times 298 times the natural log of, I'm going to use this fraction form here, 2 squared over 1 times 10 to the negative second cubed times 1.47. Okay, close that off with the parentheses, and I get 36.7. Okay, so I get plus this whole term right here is 36.7 kilojoules per mole. Okay, so now I'm going to compare that to this term right here. So these two are kind of like battling each other. So with this, what this does is it ends up putting me at, so if I add these two numbers together, I get a delta G non-standard of positive 3.41 kilojoules per mole. So that puts me right here on the curve, like a little bit past the equilibrium point on the right side. So it puts me like right here. Okay, so as we know from Le Chatelier's principle, Q is greater than K. So this number is too big. Okay, this number right here is too big, and this number is too small. So this reaction needs to shift this way to get to this point right here. Okay, and it does so by, so this number was too big and this number is too small. So when it shifts left over time when it shifts left, this number will go down, and then these numbers will increase slightly, just very slightly, because we're almost there. We're almost at equilibrium. So they just need to go up a little, or sorry, this needs to go down a little, and these need to go up a little, so that we can lower this number a little bit, so that it matches this number. So the RT ln of Q term will get smaller as this progresses to the left, as this reaction shifts to the left. Okay, so in fact, if I change these numbers to, so if I use 1.9 squared, so this is if it shifts to the left, this number should go down, okay, and then these two numbers should increase, okay, so that Q can get to K, so it can lower and get to K. So so these numbers should increase. So if I plug in the number 1.4 times 10 to the negative second cubed, and then this number goes up a little bit to 1.5, what happens then is if this drops a little and these go up as it shifts to the left, then this number goes down to 33.9. Okay, and that would put us like right here, still not quite there, but closer. So that number and that number would be a plus 0.6 kilojoules. So now we're almost at equilibrium. Okay, so you could see as this progresses to the left, this term gets lower. Okay, and while this one stays the same because this is calculated under standard conditions, so this is not changing, and this number is getting less positive until it matches this number, and then this and this are equal but opposite in sign, and then delta G would be 0 in that case. Okay, so let's take a look at the other side of that curve. So if we have this example, okay, so now in this analysis, we're going to be looking at this side of the curve, okay, and we're going to use the same reaction. So nitrogen gas and hydrogen gas makes ammonia, and in this example, I'm going to use 1.50 atmospheres. So here, I'm compared to the previous example, I want to have way more reactant than I do product. So right here, I'm going to use 0.1, which is a lot more than the last example. And then I'm going to use 2 atmospheres of the nitrogen here. Okay, so if I run this calculation, I get, Q will be the ln of 1.50 squared over 0.1 cubed times 2. Okay, and if I times this by, so take this and times it by R and times it by T, then I get for my RT ln of Q term, I get 17.4 kilojoules per mole. So if I write this out, ln of Q, okay, this is, remember, this doesn't change, negative 33.3 kilojoules per mole. Okay, and then this term is 17.4 kilojoules per mole. So here I wind up with a negative 15.9 kilojoules per mole, and that actually puts me, So here is the equilibrium position where it's 0. Okay, so if I have negative 15, that puts me over here somewhere, like right here. Um, so what needs to happen? Q is less than K, so I have too much reactant, as we know from Le Chatelier's principle. Q needs to get bigger. So that means that this number is too big down here, and this number is too small. So what does the reaction do to improve that? It needs to raise this number. Over time, this needs to go up, and this needs to go down so that Q can go up and match K. So over time, our RT ln of Q number is going to go up. Okay, so if I plug in some new numbers, so if I do this again and I plug in like 1.8, so I make this the products increase. Okay, if I do that and make these numbers go down, let's say like 0.02, so I have less reactant than I did before, times, and instead of 2 atmospheres, I'll try 1.8 atmospheres. So my RT, if I use those numbers for Q, my RT ln of Q term is going to be 30.5. Okay. And if I do, so this is my second calculation. I know it's getting a little messy here, but this would be negative 33.3 kilojoules per mole. Okay. And then if this number goes up over time, my products go up and these go down, I improve this number to 30.5. It's still not enough to get me to equilibrium, but it pushes me around right here, much closer than I was before. So here I have a negative 2.8 non-standard free energy, okay, which puts me about right here, okay. So as you see, let's go back to this slide. Our RT ln of Q term gets smaller over time. So here I had way too much product. So this term needs to get smaller to match that term. Okay, and then if you are starting on this side of the curve, your RT ln of Q term needs to get bigger so it can match this negative number. Okay, and then once this equals 33.3 positive, then you're at equilibrium. Okay, so what then occurs when you're at equilibrium? Now we have a relationship between, we're no longer looking at delta G non-standard and Q, we're looking at K and delta G standard. Okay, so when the system is at equilibrium, then we have, when the system is at equilibrium, we have this, delta G equals 0 and Q equals K. So that that equation from earlier, we set that equal to 0, and we switch out Q and call it K. Our RT ln of K. So if we move this term over, then we have delta G standard equals negative RT ln of K. And this just, so now we're not looking, notice when we look at this equation, we're no longer looking at Q and delta G non-standard. All right, I'll make a note of that, non-standard. We're no longer looking at that. We're looking at delta G standard and K, the relationship between those. Okay, when it's nothing's disturbed anymore and it has reached equilibrium. So what does this tell us about the reaction? So it says a couple of things. If you have Q, so if your delta G is negative, then if we rearrange this term, there's a real useful form of this. Actually, let me write this out. So if I solve for K, then I take, it'll be, K would equal E, because I'll have to exponentiate both sides to get rid of the natural log, negative delta G over RT. Okay, so what does this tell us about delta G and K? So if delta G standard is negative, okay, or textbooks like to say if delta G non-standard is less than 0, it's spontaneous. So this reaction is going to lie heavily to the right on the product side, because if we look at this expression, we're plugging a negative here in for this term, okay? And if you do that, you end up getting K equals E to some positive number here, and it doesn't matter what it is. So you're going to get K will always be greater than 1. Okay, and if you look at K, it's product over reactant, and that means your product amount is going to be greater than your reactant if K is greater than 1. Okay, and you could have another scenario if delta G standard is positive, and textbooks like to say delta G is greater than 0 in that case. Then if we look at this expression again, this, a positive goes in for delta G, which makes this whole term negative. So you're taking, when you solve for K in that instance, you're taking E to the negative some number. And if you go ahead and try this, just plug random negative numbers in for this, okay, and then you'll get K is less than 1, and remembering that K is equal to the ratio of product and reactant, that means your reactant amount is greater than your product amount. Okay, case number 1 commonly happens when, so case number 1, a real common time this happens is in redox reactions. They're known for having have huge values for K. And then this case happens in, some most recent examples that we've seen this happen is like weak acids and weak bases. Okay, where we know that this is true, the equilibrium lies heavily on the molecule side and not the ion side for the acids or bases. Okay, there's a third situation that can happen, and this doesn't really carry any significance, but I will mention it. This is if delta G standard equals 0, then K would equal 1 in that case. So because our term, we would be plugging in 0 right here, and E to the 0 is 1, so K would equal 1. Okay, and all that really means is your ratio of product to reactant is 1 to 1. It doesn't really carry any special significance though. We'll be mostly looking at these cases here and here, and it's really nothing new. As we see, in our previous units, most recently, we see this all the time. Okay, and then we're going to see in our next unit, electrochemistry, we're going to see this happening a lot, actually. Okay, so let's look at a couple examples when it's at equilibrium. So the relationship between K and delta G. So here we have the rusting of iron, and if we calculate delta G, so if we calculate the enthalpy for this, I'm going to get the products the enthalpy of the heat of formation of the products minus the enthalpy of formation of the reactants. Okay, then I get 2 times negative 826 minus, this would be, let's see, oh yeah, that's right. So iron would be 0, so this is 0 here. Okay, then I get this number. I get negative 1652 kilojoules per mole. Okay, and if I solve for delta S, okay, so what I'm trying to do here is solve for K, the equilibrium constant. Okay, and I'm going to use this relationship. So what I'm trying to get right now is delta G standard from the thermodynamic data here. So this is going to be the entropy of the products minus the sum of the entropies of the reactants. So this will be 2 times 90 minus 4 times 27 plus 3 times 205. So as expected, the solid metal has a really low entropy. Okay, and then the gas has a much higher entropy. So if I do this, I get this number. I get negative 543 joules per mole. And if I solve for delta G, finally, I get, it would be delta H minus T delta S. And I plug these numbers in, then I get, let's see here. So I get negative 1,652 minus, this is, we'll say it's happening at 298 Kelvin times a negative, and I'm going to change it to kilojoules, 0.4543 kilojoules per mole. Okay, then for my delta G, I get a negative 1,490 kilojoules per mole. Okay, so now solving for, now taking this, and I'm going to solve for this term right here, then I get delta G over RT. So as I was describing before, I have a negative, Okay, so as I was describing before, I have a negative delta G. It's actually humongous, negative delta G. And I plug that in, I'm going to get a positive number here. So this equilibrium is going to be some huge, huge number. Okay, so I get K equals E to the 601st power, actually. So this is the equilibrium constant for this. Okay, and this is the rusting of iron. So we have solid iron and it rusts in the presence of oxygen, and this is rust right here. Okay, so what this tells us is this reaction is not coming back. So this is kind of ridiculous to even have double arrows. So you shouldn't even need that. It should just be a one-way arrow here. Okay, because the rust is not going to come back and turn into these two things. It lies heavily, heavily, heavily on the product side when we do that. Okay, so I wanted you guys to try that same analysis for these two. Okay, so in this one we have the combustion of octane. So make sure you write a balanced reaction so that you can calculate this right. And then here we have the dissociation of acetic acid. So one reaction we know it's burning is making gases, and we know that those gases aren't going to come back and make liquid gasoline again. And then compare the result to what happens here and what we know about the equilibrium of weak acids. Okay, so it says in question 3 here, it says comment on your results. What's the connection between delta G and equilibrium? Okay, so that's the end of our video.